Hello everyone, my name is Povilaitis and I'm once again presenting the solutions to MIFMO 2026. And as you can see, this is problem number 3, so if you haven't already seen the videos to problem number 1 or problem number 2, I recommend you go watch it. Problem number 1 was about constructing a polynomial of some sort, and problem number 2 was basically constructing a certain number set with certain properties and requirements. And yeah, so this problem is not that difficult either. It's pretty basic in terms of the theory and the background you need to know. So it is quite doable, I guess, and especially compared to the first two problems. So, okay, we get this problem, and what do? Let's say we have no ideas. Well, we can try different values. We can try which values of a seem simple, right? Because we need to find, basically we need to calculate this integral for every a, and also we need to prove that it's convergent for every a. So finding its value for every a, which values of a seem simple? Well, for me, the first idea is a equals 2, right? Because then the bottom of the fraction is just sine x squared plus cosine of x squared, which is just 1. And we get that this integral is just cosine x squared dx. And you can try calculating this integral. I'll leave it up to you. For example, for a equals 1, we'd get that this integral is just cosine of x sine of x plus cosine of x dx, right? So, well, we do that, but it's not really that simple to see anything further. It's not that, oh, the answer just pops out immediately, right? So this doesn't seem like a very likely approach, just plugging out different values and noticing something. You can try, of course. So then, what are the most common tricks with integrals? Well, the first one is, of course, integration by parts. Well, of course, before integration by parts is just guessing the mother function, but that doesn't seem likely here because it doesn't seem that simple. And yeah, integration by parts doesn't seem that easy either, because, well, we need two parts, right, that match their derivatives quite nicely. And yeah, it just doesn't seem that likely here, because this denominator is still very, not that good looking, and I don't see any way of putting it into a nice part and splitting the integral so that it simplifies. I think it would just mess up the whole thing. So this trick doesn't work. Well, this trick, yeah, it probably should work, but I don't want to get super delicate with it. So our basically remaining trick is what? Do a substitution, right? Well, the most common tricks with integrals are integration by parts or some substitution. Substitution, right? Which substitution seems likely here? So we have this integral, right? Cosine of x to the a divided by sine of x to the a plus cosine of x to the a dx. So basically, you can see that this function is periodic, right? Because cosine of x has period 2 pi, this has period 2 pi, this has period 2 pi. So something to do with periods doesn't seem that that unlikely here. So especially, I suggest you remember that a very common substitution trick, especially for trig functions, so trigonometric functions, which are cosine, sine, tangent, the substitution is that you let t equals pi over 2 minus x. Or yeah. So I'll just do this substitution here. Well, what you do is, yeah, let x be pi over 2 minus t. Yeah, because these are the same things, right? You just move these two around. But yeah, so yeah, we might just yeah, okay. I was trying to do this, but I wanted, yeah, basically you must remember that if you do a substitution of any sort, you must change the bounds. That is a must, because otherwise, basically, it's just, yeah, you can't proceed from there. If you already made this mistake, basically, there's no going back. So when x equals 0, right, this side also has to be 0. So t equals pi over 2. And when x equals pi over 2, this side has to be pi over 2, so t is 0. So basically the bounds just swap around. So you get pi over 2 here, and you get 0 here. And okay, so now rewriting everything, we get cosine of pi over 2 minus t to the a divided by sine over p over 2 minus t to the a plus cosine of pi over 2 minus t to the a, and don't forget to change the variable here, d pi over 2 minus t. Oh, this, yeah, this might have gone. Yeah, I'll just write it here. Yeah, I don't want it to go over the camera. So yeah, we have this. So this is equal to what? Well, now we want to simplify everything. So just for the sake of simplicity and not wasting your time, I've already prepared these formulas. Basically, these are trigonometric formulas that, well, these are also very well known in school and also quite often used in university. So, but yeah, I think everyone is familiar with these formulas. So cosine of pi over 2 minus t would be what? Would be cosine of pi over 2 times cosine of t. This is a minus here, so this becomes a plus, right? Plus sine of pi over 2 times sine of t. So if you remember, maybe I'll sketch out the graphs. But sine of 0 is 0, right? And sine of pi over 2 is 1. So this would be the sine graph, right? This is y equals sine of x. And for cosine of x, it's just this, right? And this would be y equals cosine of x. So at pi over 2, cosine is just 0. Well, these numbers must be, yeah, this is pi over 2. And yeah, this is 1. So at cosine and at pi over 2, this number is just equal to 0, right? Because 0 times anything is 0. And sine over 2 is 1, so this is just 1. Okay, and as for the sine, this, well, we use the same formula. Sine of pi over 2 times cosine t minus cosine t times sine, minus, these are written very, most of the time it's just written, okay, these are quite weird because most of the time it's sine a times cos b plus sine b times cos a, so I messed it up. So this should be cosine of pi over 2 times sine over t. And we want to have, once again, have the same thing. This disappears, right? Because this is just 0, this is 1, and this is just cosine of t. And the final thing to simplify is d, the derivative, or the, So this is just what? Basically, we need to calculate the derivative of this function. So this would just be minus dt. I don't know what's happening. This is just minus dt because the derivative of minus t is minus 1. So finally, we've simplified everything. So now, rewriting everything that we have, this is pi over 2 of 0 would just be equal to what? To cosine, cosine of this number would just be equal to sine t, right? So this is just sine t of a, and in the bottom we have cosine of t a plus sine of t a, but we have a minus, right? Because we got a minus. So what happened? Well, the thing that happened is basically the integral, right? It's just the area under a certain curve. But if we are calculating from this point, basically, if we want to change the boundaries, we just change the sign. So this is in fact just equal to, we change the sign and we swap around the boundaries. So this is 0 to pi over 2 and sine t a cosine t a plus sine t a dt, right? But look what we've shown. We've shown that this integral, right, is equal to this integral. Yes? And just to don't mess things up, this is basically just known as a demi-variable. So, well, you could just write x instead of t, right? Because, well, dt is basically just the same as you rewrite t everywhere. So it's not that important that it's a t instead of an x. But we've shown that I of a is equal to j of a. We've shown that already. But look, what if we calculate I of a plus j of a? This is just the integral of cosine x to the a divided by sine of x to the a plus cosine of x to the a, right? I've written this integral, but look, this integral has the exact same, I think, denominator, the bottom of the fraction basically. I'm mixing them up once again. So we can just write this here. Sine x, yeah, to the a. And this is the dx. Don't forget dx. Do not forget dx ever. And this is what? This is just the integral of 1 dx, which is basically x calculated at pi over 2. Yeah, this is just pi over 2, right? So what do we have? We have that 2I of a is the same as I of a plus j of a, right? Because I of a is the same as j of a, but this is equal to pi over 2. And dividing by 2, we have that I of a is pi over 4. So what we've actually shown is that the integral is equal to pi over 4 no matter the constant a. But so that's, it looks like we've shown everything, right? We've proven everything. Not really. We haven't done anything about the convergence. And yeah, this convergence, even though it seems super intuitive that it's convergent, we still need to show it. And as a matter of fact, it would actually have been better to have started with proving that the integral is convergent and then and only then proceeding with these solutions. But look, proving convergence is not that difficult. I mean, it's not even a proof. Well, we have this integral, right? Yeah. So, okay, I'll name this function f of x. The inside of the integral. Then f of 0 is what? Is cosine of 0, which is 1, divided by 1 plus 0, which is 1. And f of 1 is 0 divided by 0 plus 1, which is 0. Or not f of 1, but f of pi over 2. So look, these boundaries are also finite, right? It's not that the integral goes to infinity or something. This is from 0.0 to pi over 2. It's a bounded integral. We just need to show that the function x is bounded. But this is very simple because we can just write this inequality. Cosine of x to the a is between 0 and 1, right? Of course, in the interval when x belongs to 0 and pi over 2, right? So this inequality is true because all of these things are non-negative. And this inequality is true because if you multiply, because sine of x to the a is non-negative. So what we've shown is, well, so this is just basically how do you come to the solution? But if you wrote an official solution, well, how would you start? You would first claim that, oh, let's prove that the integral is convergent. How do we do that? Well, we say that at the boundaries of the integral, the function is finite, right? This is 1 or 0, 0 or 1. And yeah, the values of the bounds are also finite, and the function itself is bounded. So basically it's then you can just state that obviously the integral itself is convergent because it doesn't have any discontinuities. Well, and then you do this substitution, and yeah, you just finish. The main idea, well, when you get the problem of such sorts, I have two comments. First of all, it's very common to think about this plus sine of x to the a. So it's very common to add this tool to your repertoire, because it's very common to basically, yeah, because it's really hard to find this integral just by calculating. So you'll need to do some trick, and most of the time, well, it would be super easy just to write sine of x, right? And the bottom and the top cancel out, and it's just 1. What's the harder part is showing that these integrals are just equal. But this is very easy by this substitution. So what I suggest you to take away is, it's very common, especially with problems with trig functions, cosine, sine, mostly these, it's very common to use this substitution. So yeah, don't forget it, because it's used very often. So yeah, that's it for me. I'll be waiting for you in the fourth video, not the final one of this Olympiad, but we'll continue onwards. So yeah, thank you for watching and have a nice day. Bye.